All right, so now that we have parabolas out of the way, we can start talking about ellipses and circles. So this is going to be different than how you dealt with circles in the past. It's still relevant. Ellipses are ovals, but they're ovals in a different way. So ellipses have two foci. And we'll talk about that where circles have the one radius. So we saw how what a focus is with a parabola, and we'll talk more about that when we talk about ellipses. So let's get into it. So in this lesson, we're going to explore ellipses and circles and their graphs. Good job, Edmentum. um, I feel like they need to get a little more detailed with it, but I think they're just not doing the state standards for it. So we're gonna see ellipses again. Watch the video; they do a much better job of explaining ellipses than I do. But they do occur in nature, like you saw right there with the sun and the planet. So you see that here. Um, the word eccentricity would describe a person's unconventional beliefs. So um, we're just going to be talking about centers and things basically. Again, they do a much better job of explaining how this can be applied and the history behind it than I would. So I'll leave that to them. You've learned conic sec. So we've learned about how everything in conics can be done with a double cone. We'll have every shape possible, every conic possible. So let's get into circles. So the standard equation of a circle, remember that HK is always our center, R is our radius. So the standard way we see a circle is any x value minus the center squared plus any y value in the circle minus the y value of the circle's quantity squared equals the radius squared. This is probably the most useful because it tells us how to graph it by having the h and k here. So the reason why we subtract it is this kind of helps us figure out where the x value is in respect to the circle. And what this essentially is, it's the distance formula. It's the this is your y minus k. This right here is your x minus h. So what you're doing is you're squaring them. A squared plus b squared equals your c squared, which is your radius. So essentially what a circle is the Pythagorean theorem. So if you guys ever wondered like where when you use the Pythagorean theorem, it happens a lot when you're dealing with circles. Um, but I'm sure you guys have we've used the Pythagorean theorem before when we are doing trig, but this is one where it occurs a lot more often in real life. We see it with circles rather than with trig functions. Next form is the general form, which is essentially just polygon in standard form. So this is how we see it polygon wise, except the y values are kind of in the mix this time. So it's not really a function. So I guess calling a polygon isn't accurate because a polygon is a function. This is not. And then there's expanded form, which is where we essentially have this equation just expanded out. Um, Not sure how that's as useful. I'm sure they'll kind of talk to it, but expanded form is basically we take the standard form and spread it out and combine all the numbers together. They're also like keeping this h squared and k squared separate, so it's not one big constant like it is in this form right here. All right, so let's get into this a bit more. So, keeping in mind what we saw about the equation of a circle, so we can say here that our center, looking at this, is going to be 2 comma positive 1, and the radius is 1 unit. So if we look at a different circle, and again, this thing's kind of in the way, I'm sorry. We see here that this center is at 2 comma 1. Oh, it's the same one. Sorry. And the bottom circle. Okay, so here's the bottom circle. And this says, oh, I see. If you look here, they are tricking us a little bit. See how we're not squaring it? I think this is, yeah, it's talking about the placement of the squared. So if you see here, there is a parentheses, but they're tricking us. This -2 would actually come over here because it's not with the squared. This -1 would actually come over here. So in reality, what we're looking at is if we move this 2 over here to the right side of the equation and this 1 over, we're looking at x squared plus y squared equals 4. So in this case, the center is 2. So that's just teaching us about the placement of parentheses. This placement of parentheses shows us a huge difference. The radius is different. The center is different. So make sure you're paying attention to the placement of parentheses. Also, if it's a plus sign instead of a subtraction sign, we get a completely different shape. So right here in the center, instead of adding it, we get an ellipse or not an ellipses, hyperbola. Uh, so a hyperbola, not to be confused with hyperbole. I always get those two confused. So hyperbola, hyperbola is this shape. It's kind of like this inverted ellipses where we still have two foci, they're just going in the exact opposite direction. So you definitely don't want to put a minus sign right here in the middle. It completely changes what we're talking about. So placement. So this is just showing what can happen when you change your formula even a little bit. Another thing that can happen is, let's say you have the formula but it's not squareable, I guess would be the right term, because you can technically multiply this by the greatest common factor, and simply by having a non-squareable radius, um, you end up having an ellipse. So this is how we get an ellipse: is the r is essentially not squareable. The distance is always changing, and we'll see how this is affected later. So if we're looking at this, we want to figure out the equation of the circle. So we know it's not this one because if I were to, let's see, this is 4, this is 9. If I multiplied both sides by 36, oh, actually, they're tricking us here because, well, let's get into it a little bit more. Let's write this equation and talk about it a little bit more. So if I wrote this equation, my center, my HK is 1 comma 1. My radius is a distance of 1. So if I wrote this, it would be x minus 1 quantity squared plus x minus 1, or y, sorry, y minus 1 quantity squared equals 1 squared. So let's see if we can find that formula. And that would be this one right here. Now, one thing that I was going to say too is this one's kind of tricking us because this actually uh, it it is a circle. It can be seen as a circle as well. It's just when we divide it. So because even if we multiplied all of this by 36, we would end up getting x squared plus y squared equals 36, which looks like a circle. Um, but how it's written and how it would behave would be different just because of how it's written down. But again, we'll get into ellipses a little later. All right, so now well, later has come apparently. So when we're talking about ellipses and their equations, there's two foci. So if we had two thumbtacks on a piece of paper and we were to draw a line, so we pin this little line string in between it with some slack. There has to be slack. They're saying keeping this. We put the string in the middle of it, and we stretch it out till it's taut, meaning till this is tight, and we can just draw around it. We would get this ellipse. So we would drag the pencil around this, and the string, you would have to switch here. Once you get to here, you kind of have to switch, go to the bottom, and draw it again. You would end up getting this ellipse. So I have a feeling they're gonna make us draw it just like they did with the parabola again. Um, Again, I don't have the tools to do that. So if we have to do that as an activity, we'll do what we did on Desmos. That one kind of threw me for a loop. So I'll make do with Desmos. But in doing this, we have what's known as two foci. There's these 2 points that are essentially anchoring down the distance that can happen here. And by doing this, we end up getting what's known as 2 axes, a minor axis and a major axis. So the major axis is where these foci line up. The minor axis is essentially a perpendicular line, so a line perpendicular to the major axis that has the, how can I describe these? They're not vertices because these are vertices. The vertices are on the major axis. I guess the maximums and minimums of that axis. I honestly don't know how to describe it, but we get these things right here. It's the short side versus the long side of the ellipses, basically, is what I'm trying to say. All right. So let's kind of go in here. So now let's identify these. So these parts right here, these two would be the foci. So the foci, just remember, are on the major axis. Um, and they're kind of what anchors that string to that piece of paper. So I'm going to call those the foci. Where's my check mark? Oh, I guess I don't get the check mark until I click done. This little dot right here is the center. The center is going to be where we find the major axes and the minor axes crossing each other. So I'm going to call that the center. This part right here, it's not how we normally look at it, but it is technically a vertex. So this is a vertex right here. It is the most left, the most right, or like basically it's the extreme of the major axes. Like I said, there's no name for the extremes of the minor axes, but there are names for the extremes of a major axis. Extreme meaning that the maximum or minimum of that axis, of the major axes. So this would be an extreme of this line. It's the most left. This one would also be a vertex, although they're not labeling it, because it's the extreme of the other direction. So the next one we're looking at is, you see that they're pointing at this line right here, the short line. That would be known as our minor axes. So we're going to call that our minor axes. And then we have a line or an arrow pointing at this long line. That's our major axes. All right, so let's click done. And we got them all correct. Perfect. So moving on. So what's essentially happening right now, when we're looking at a ellipses, is any point on an ellipses, there's this distance formula, but there's also a distance formula on the other side of the parabola. So you have to view it as having a distance formula. And we have these 2 points. And we're talking about the distance from HK, obviously. So this AB, this um, B squared, is the distance, let's call it the Y distance. This is the Y distance, the vertical distance. There we go. The B is the vertical distance of any point on the ellipses. And the c in this case is the horizontal distance of the ellipses. And this 2a, where are we talking about? Oh, a would essentially be the distance um, from the center to the ellipses itself. So they're getting this formula that this point right here is twice. There's 2 points right here. There's 2 distances, and that's going to be equal to twice the distance from here to the vertex. Oh, that's what A is. I'm sorry. A is not a point to the ellipses. It's a point from the center to the vertex. And you know what? If I would have been reading this, I would have had that fine. Yeah. So the vertices are the distance A plus. So A, the value of A is the distance from the center to the vertex. And again, I could think I kind of butchered that. If you need it in writing, I recommend going through this and reading it a bit. But C is horizontal distance from, well, we don't need it. They're variables. You can see the picture right here. And they'll talk about it in here. I'm sure it's a lot better than how I explained it. All right, so let's kind of get into this. So if we're talking about distance in general, here's our distance formula. That's a general distance formula. But the thing is, we're talking about 2 different distances. So because we have 2 different foci, we're going to be talking about 2 different distances. So what we're doing here is, in order to account for the fact that we have 2 foci, we're going to double A. We're going to talk about them twice. So there's a distance there and another distance to the other foci. And what we're going to do here is we're going to square both sides. So what are we doing here? The equation we get from the 2 cycles squaring both sides. So if we were to square both sides, we would get this. So I feel like they've kind of missed some things here, but they're just showing us they're skipping a lot of work, basically. And we're going to get all of this here. So this 2 would eventually cancel out or with something once we square it. And then we're going to substitute b squared. So we substitute in the h minus c for the form. So this is us just subbing in. This x is our just any value of x on the circle. This h minus c is here versus the h plus c, which would be on the other side. So this is h plus c, this is h minus c. So it's talking about both the distances from each of them. All right. And then we're going to substitute in with b squared, we're going to do a squared minus c squared. So a squared minus c squared. So a squared and then minus the c squared to figure out this distance of b right here. So this is our c and this is our b squared. So that's just this part right here. Once we substitute those in, we can see that we get this. So proving it is something you kind of have to learn. I would review it a little bit, see if you can understand it. The moment you can kind of understand it, you should be on the right track. But this is something you might want to study for the mastery test. So I would definitely put like a little bookmark here, see if you can understand it. I don't think I can give it justice. It's just something you kind of have to do it on your own and practice it. If you have questions, feel free to leave them in the comment section. I can try to clear up any misconceptions you guys might have about it. So we also have vertical and horizontal ellipses, kind of just like we had for parabolas. So the a, it's important to note that this a should always be the value of your major axis, half of your major axis technically, and b should always be the value of the minor axis. So if we see a big a, or if we see a big number, like obviously, let me just make up an equation for one right now. Let's say I do x minus 2 quantity squared over, I'm just going to have squared numbers here. So 4 plus y minus 1 quantity squared over 36. I see here that my y has a bigger value underneath it. So this tells me that this is a vertical ellipses because the y value, my horizontal coordinates, have a uh, bigger axis at the bottom. All right. So that's how you can tell if the number underneath the x is bigger, you're talking about a horizontal ellipses. If the number in front and the number underneath the y is bigger, you're dealing with a vertical ellipses. All right, so let's take a look here. So if I'm looking at this, I'm trying to figure out is this a circle or a non-circular ellipse? So the easiest way to tell is if our A and our B are equal, then it would be a circle. So this one, our A and our B are not equal. We're dividing it by two completely different numbers. Then what's going to happen here? Oh, this is actually what I was talking about before. I don't know if they mentioned it and I glossed over it, but if you were to multiply but the lowest common denominator, you would have a number in front, a coefficient in front of either coordinate. So if these two numbers are not equal, it ends up being an ellipse. So you can just drag this here because we know they're not equal. Let's see if, oh, A and B are not equal. I feel like it's giving this away for these. So if your A and B are not equal, what's going to end up happening here is they're saying like, oh, let's divide everything by A squared and B squared. Oh, I'm sorry, not plus. That'd be super hard to do. Let's divide everything by a squared, b squared, divide this by a squared, b squared, divide this by a squared, b squared. What'll happen is the b's would cancel out and you're left with an a squared at the bottom. This one, the a's would cancel out and you're left with a b squared at the bottom. And then you get some general number here, some constant here. And I say constant because A and B are constant numbers. We just don't know what they are at the moment, which I guess would technically be a variable, but it's a constant for whatever parabola we're talking about at the time. So the fact that they're not equal means that this automatically has to be an ellipse. Now this one, it looks like you would think that this is a parabola, but in reality, you can factor this out. Like if I did a box method, I could technically factor this out. Put an x squared here, put an h squared here, and I have a negative 2xh here. If I do x squared, x and a negative h and a negative h, I end up getting this negative xh, negative xh. I would get this x minus h quantity squared because I have an x minus h here and x minus h here. This one's a little tricky. It's something you kind of have to spot. It comes from the idea of um, essentially having the, if you ever have a negative 2 times AB in your center here, meaning that this is your A term, this is your B term, it's going to be a perfect squared. So this is a perfect squared, and then we can see here that this So this is a perfect squared and this is a perfect squared. Sorry, I forget that sometimes when I'm writing with my uh, pen, you guys can't see it. So I forget to go over with the mouse sometimes. So then we're seeing that this is a perfect squared for the x and that this is a perfect square for the y. So these being perfect squares mean it has to be a circle. And I feel like I'm going on way too much about it. I'm sorry, but I just want to make sure that's clear. If you look at this one, this gives you a perfect squared. So if I'm looking at this, that's a perfect square. That's x minus h quantity squared. And I have a negative 2 here. If I look at this one, I can factor out the negative, and then I have y squared minus 2yk um, plus k squared. So this is also a perfect squared, y minus k quantity squared. You can bring this over, bring that over. So this, even though it's going to end up being x minus h squared plus y minus k quantity squared equals 2, even though square root of 2 is a weird radius, it's still a radius. So that is actually a circle because we can get those perfect squares in. It's just kind of ironic to think that the way we get circles is from squares, but that's how it works. It's a perfect circle, so you have to have those perfect squares. Now let's talk about graphing an ellipse. So graphing an ellipse is kind of interesting. So you do need to know where your center is. Essentially, the way I always graph an ellipse, I don't know if they'll talk about it here, is what I do is I have to plot my center, and then I figure out what my A is, and then I go, oh yeah, they're actually showing it right here. My A squared equals 9. So therefore, my A is equal to plus or minus 3. So I have to go 3 to the right, 3 to the left. And the only reason why I'm going to the right and to the left is because we're talking about my x coordinate here. This one, b squared equals, and the only reason why I'm using a and b is because this number was bigger, so I called it a. This number was smaller, so I called it b. So therefore, b uh, is equal to plus or minus 2. And since it's underneath the y value, should probably use different colors for these. It's underneath the y value. Let me just erase all of this. So, because it's underneath the y value, we know that this is going to be how we control our up and our down, our vertical. So I would go 2 up. This is like the worst color for graphing. This down, at least coloring graphing on a blue background. Let me do it in purple or darker blue. There we go. All right, so that's how you would end up graphing it. And then you kind of just curve it on there. Obviously, it has a specific curve, but if you're just sketching it, that's a good way to kind of sketch it. My graphs were always terrible when I would graph ellipses. All right, so let's keep going. All right, and when you're graphing, so again, this is pretty easy to do. You graph your center, square root of, so if you look here, the number underneath the x is not an a, it's small. So that's why it's only 2. So that's why we have a b. This b is 2 because x has a smaller number. And in this case, the 16 is our a squared because it's a bigger number. So the square root of 16 is 4. So we go 4 up and 4 down because they're underneath that. And there was no h and k. So because there was no h and k, our center's the origin. All right, so let's graph an ellipse. Let's see if this ends up being complicated. All right, cool. They're letting us use these. So if we look here first things first, we want to know what our center is. So our center is -3, comma, -2. So that's why you see that there's a lot more room over here on the negative side. We see that it is going to be, we have a bigger number on x, so we know it's a horizontal parabola. You don't really have to identify it. You realize it when you're like, oh, x, bigger number, you graph this. So you're going to say that a squared equals 16, ergo a is equal to 4. You're going to say b squared is equal to 9, ergo a is equal, or b, change my variables there, plus or minus 3. This should be plus or minus 4 to be technical. So when we graph this, I'm going to go here, grab my little pencil. It's not letting me do it because I'm using different software, so I'm just going to use my regular pen that I use to show you guys. So I'm going to go here. I'm going to graph a center. You could technically try to use these. Not recommended. I don't recommend it. It'd be really hard to graph. You could try to overlap it later. I don't know how this works. I think how it works is like you pick a dot and then it kind of like expands out. I don't really know how to do it without showing you guys. But I honestly just recommend using this little pencil right here and plotting your dot. So we're going to go -3 on the x, -2 on the y. So we put a little dot here. And then what we're going to do is we're going to go to the right 4. So 1, 2, 3, 4. And we're going to go to the left 4. So 1, 2, 3, 4. You can see they gave you barely enough room to graph the horizontal. Then for the y value, we're going to go plus or minus 3. So we're going to go 1, 1, 2, 3, 1, 2, 3. And then what you do is you're going to kind of just draw this here. Try to include those dots, kind of curve it in. I am terrible at drawing, so I apologize. But now you guys get to see how terrible my drawings are. They have not improved since high school. And you can see how they're doing it right here, the exact same way. So let's take a look at this one. So if I look here, first I'm going to identify my center. And my center in this case is going to be a 0 for the x because I don't have an h here, and 4 for the y. And then if I look here, this is going to be a vertical parabola. And that's because the y has a larger number underneath it. So when I'm graphing this, I'm going to identify a squared to be 16. So a is equal to plus or minus 4. And we say b squared is equal to 4. So my b is equal to plus or minus 2. So when I graph this, I'm going to go 0 on the x and positive 4 here. And I want to go plus 4, minus 4. So minus 4 would be down here. Plus 4 would be over here by the 8. I'm going to switch to do my horizontal. So that's going to be plus 2, so positive 2 and -2. It works out that my h was 0. And then I'm just going to draw this. I'm going to circle this, how this is encompassed here and here. I feel like parabolas have so much to describe that they feel complicated. So when you get to ellipses, it feels a lot better. All right, so let's move down. So do your evaluation, see if you understand how to identify if it's a vertical parabola, if identifying if it's a horizontal parabola. If you're still having trouble with that and your circles did not come out the way they were intended, let me see if it lets me draw here. Oh, this one does let me draw. So the way I recommend doing this, I'm gonna reset everything, is you're gonna draw your circle, go here, if you can. Oh, let me see if they lets me do the ellipse. So if I start at the center, this is the thing I don't like about it. You're gonna have to identify your radius first, your vertice first. So if I tried doing it with this, I would go like this. But even then, it's really hard to do. So I could do this and identify my major axes. So like this. So it's kind of weird because you would have to super understand how to do it. If you can do it, like that's great, but I feel it's very time consuming because what you have to do is you have to identify the minor axes. So you have to go here to the center, go two over, go up to right here, and then just go down until you get to right here, kind of combination. So you kind of have to do this combination of the major axes and the minor axes. You're going to both extrema here, and you have to go down to the other extrema here, and you would get a perfect ellipse if you can do that. So you literally have to go to h plus b in this case, comma y, or I'm sorry, not y, k plus a. Oh, actually, I did those backward. No, I did those correct. That, and you have to go all the way down to h minus b, comma k minus a. It feels weird, but it is possible. You saw me just do that right now. Boom. Little weird, but it is physically possible to do that. I actually like that. I might do it myself. You can also write down like, oh, it's really hard doing this with the actual ellipses tool or ellipse tool. There's not multiple of them. All right. So let's see what else we got here. So let's identify this ellipse. So first thing I have to identify my major axes. So my major axes is along the x-axis, so that works out. And I'm going to 6. So I want to cut my major axes in half. So the distance from vertice to vertice is going to be 6. So the center should be right in the middle and along the major axes. So my center is 3 comma 0. And my A, so because it's a horizontal parabola, my A is going to be 3. So it's going to be 3 squared, which is 9. And then I'm going to have x minus my h squared. And I'm going to add my y minus my k. Well, there is no k, so I can just square my y over my half of my minor axes. So my minor axes is, well, I can just, luckily it's along the x-axis, so I can just say this distance is 2. So 2 squared would be 4. I'm not doubling 2. I'm not doing my minor axes. I'm squaring half of it. So that's the weird part. You have to take your minor axes, divide that by 2, and then square that number. So what we're going to do here, so here's my coordinates. So I see that is this one. Oh, one thing I forgot to mention is this is always equal to unity. Um, uh, Not the game server we're talking about. It's always going to be equal to 1. Your ellipses, the equation for an ellipse should always equal 1. It should always equal positive 1 to be exact. So just a little brief there. Is that it should always equal positive 1. I forgot to mention that. I think I just glossed over with all the other stuff we were learning. All right. So if we're looking at this, sometimes you encounter an ellipses that is not in standard form to do this. So you have to complete the square. So in order to do this, let's say you have a weird shape like this, you're going to divide by oops. I had to unplug my computer to reset it because there was a lot of overbuilt static and it slowed it down. So you want to divide by the LCD, or I should say, not LCD, but no, yeah, LCD. You want to divide by the lowest common multiple / lowest common denominator of your coefficients. So by doing that, I'm going to be dividing this by 9. You also want to expand out. So first, you're going to have to complete factor out, factor anything in front of your leading coefficients. Leading coefficients being your x squared and your y squared. So factor those out. Factor anything there. And then you're going to complete the square. Then you have to divide by the LCM of any coefficients. So first it's factor from y's and x's. So x squared and y squared have no coefficients. So you want to do that. That's your first step, is factor. So you have nothing in front of the x squared and nothing in front of the y squared. This parentheses doesn't matter because we're going to distribute that. Step 2. So step 2 is complete square. Square. So you want perfect squares here. These become these perfect squares. Complete square for x's and y's. And that's going to lead you to be adding these numbers here. Keep in mind that if you have like whatever you add here has to get multiplied by whatever the coefficient. So whatever you have here has to get multiplied by the coefficient here. So that's how come they show that right here, this 9 times 4. You didn't create a 4, you created a 36. So they're kind of showing that here. And then you have to divide everything by any coefficients here, the LCD. So this one is 1, this one's 9. So the LCD would be 9. So we're dividing by 9. So this is how you end up getting this ellipses. All right, so let me clear this out. Hopefully in practice this will make a little more sense. All right, and sometimes you have it in this weird form. So here's more practice basically. Make sure you get rid of your constant first, then you're going to factor out anything. You're going to group them together. I think I forgot to say that. You want to group your x's and your y's together. So see here how they're kind of separated. You see how they put them together here. They kind of put them together and factored. Makes it a little confusing, but they basically skipped the step where it was like 4x squared minus 16x plus y squared plus 2y equals negative 13. They skipped that, went straight to like, oh, they're together and we're going to factor. From there, you're going to complete the square. So that's where we create this 4. Half of negative 4 squared is 4. Half of 2 is 1, squared is 1. So that's where we get this 4 times 4 because there's a 4 in the coefficient. This one doesn't have a coefficient, so you're just adding the 1. Because you can't create these numbers out of nowhere. You're taking the b term, the number in front of the x or in front of the y. In that case, these numbers. You're cutting it in half and squaring it and adding it here. And that's what's happening here. All right, so we get that done. We get these coordinates. I almost forgot. We're going to divide by the LCD. I don't even call it an LCD. I would just call it a CM or CD. Um, because it's the greatest common multiple. It's a common multiple. It doesn't matter what it is. It'll correct itself later. So I would honestly just do the not even the I would actually do the greatest common multiple instead of the least common multiple, which is not really a thing, but well, it can't be the greatest. So it'll literally just be you multiply these two together, this 4 and this 1, and you're going to divide by that. That way you don't have anything here or anything here. So you do that, and that'll get you your standard form. And it should always equal 1. Otherwise, it is not an ellipse. All right, so let's get into this. I'm debating on if I want to save this for the afternoon. Okay, it's one problem. So we'll finish this one off, and the next one will just be a short video later. So here's my formula. Well, the first thing I want to do is I want to separate these. So I want to do 9x squared minus 45x plus 16y squared minus 64y, and this is going to be equal to -1. So the first thing I'm going to do is I'm going to cut my b terms in half. So that is negative. Oh, wait. Before I do that, before I even do that, I forgot I have to factor out. So I want to factor out this 9. That gives me x squared minus, and this is a good reason to do this. It really makes the numbers a lot simpler to do. And then plus 16 y squared minus 4. I kind of just have these memorized. So if you're like, how is he doing all of this? Just memorization. And then I need to cut 6 in half and square it. So 6 in half is -3. Square it, it ends up being plus 9. And then I need to cut 4 in half, which is -2, square it, which is +4. So I'm going to add, remember, you're adding, so to this -1, I'm going to add 9 times 9 times 9. And I'm also going to add 16 times 4. So when I do all of this, I end up getting this number, x minus 3 squared. So if you take half of your b term, you get a perfect square. That's why you take half of it and square it, because it ends up giving you a nice perfect square here. Plus 9 plus 16, half of that squared. So this is x take away 2 quantity squared equals, this is 81. This is 64. So give me a second here. Let me grab a calculator. 64 plus 81, take away the 1. We get 144. So this is equal to 144. And you're going to end up dividing this by 9 times 16. You're going to divide this by 9 times 16. So what happens here is this 9 cancels out with that. We've seen this before, except we did it with variables. This 16 cancels out with that. And then whatever 9 times 16, I'm willing to bet is 144. Yep. So you end up getting this x minus 3 quantity squared over 16 squared plus y x y. I don't know why this isn't a y. Minus 2 quantity squared over 9 is equal to 1. So this tells me that this is I don't know why I put squared there. It should have been a 4 if I wanted to square it. This tells me that this is a horizontal parabola, not just because of the fact that I see that there's more room on the x than there is on the y, but because this x has a bigger number than this y. So when I want to graph this, I have to identify that this is a 3 comma 2 for the radius. A is equal to plus or minus 4, and my b is equal to plus or minus 3. So I'm going to go here. I'm going to go 3 and 2. So I start off at the origin, plot my graph, and I'm going to go plus 4 on the x, because if you square this, I'm going to go plus 4, 1, 2, 3, 4, minus 4 on the y, 1, 2, 3, 4. And now I'm going to do, or I said y, I'm still doing it on the x. Now I want to do my y. So I want to go plus 3 on the y, 1, 2, 3, minus 3 from the center, 1, 2, 3, and you get this right here. All right. I'm not sure how they want you to graph it, to be honest, because you can't write on this as far as I know. So you would actually have to delete this. So you would write it in standard form, which is this form right here. And if you wanted to graph it, what you would have to do is delete this picture, go on Desmos, because they didn't give you the tools to graph it. I can't believe Edmentum oversaw that. I can't even see how you would graph this. There's no writing tools here. Definitely write that in the evaluation. You would have to delete the picture, come to the graphing calculator. So you would have fraction plus fraction. I'm just hitting the division sign to make these fractions equals 1. You'll have this, what was it, 16, 9, parentheses, x minus 3, quantity squared. What was it, y minus 2? Yeah, y minus 2. You might start seeing it start graphing right now. Y minus 2 quantity squared. There you go. And you could take a snippet of this or a screenshot and then add it to whatever you wanted to do there. I really don't know how they wanted you to graph it. Wow, I feel that's a huge oversight. So talk here about how if you're struggling with completing the square, mention that. Like I have trouble with completing the square. I have trouble knowing how to graph it, anything like that. This is a really good time to reflect on that information. So I'm going to leave this right here for right now. It looks like this should only be a two-parter. Um, I've been known to get that wrong before, but hopefully that'll help. I apologize for the videos being a little late. If you guys are subscribed to the channel, you'll see that I'm putting out the videos for algebra, geometry, algebra 2, and then pre-calculus. So um, the goal is to always have these weekly, but there might be delays. So just keep that in mind. It is to have it weekly, but you can see when the videos are going to come out based on what videos have been out. I'm going to try to post every weekday, but it honestly depends on my schedule. All right, guys. Hopefully this helps out. If you have any questions, again, feel free to comment.